Hello, welcome back to the wonderful world of physics. This is chapter 15 on fluid motion. In this section, we're going to look at section 3, Archimedes' principle and buoyancy. You see here this picture of an aircraft carrier, and we're going to explore how is it that a ship like this can stay afloat in water. It's a big hunk of steel. It's over 100,000 tons. It's got aircraft on it. Every one of those aircraft is something like 16 tons. It generally has about 6,000 people in it and all the other materials. So how does it stay afloat? And we'll get to the answer in this video. In a previous video, I showed you, as you can see in this picture at the top, if you imagine in a large body of fluid, like water, imagine that there is a small sample of water that I've shown in this with this dotted lines. And if it's in hydrostatic equilibrium, it's not going anywhere. It's not accelerating. It's just sitting there in the larger volume of water. And so all the forces need to be equal. And the left and right forces have to cancel out. So there's pressure on the left, pressure on the right. There's pressure from the bottom, pressure from the top. Remember that gravity is pulling it down. So as I showed in a previous video, there's got to be an added pressure that is pushing up. And what we found is that there is greater pressure on the bottom that supports the fluid's weight. So the deeper you go in the fluid, the greater the pressure. Now we're going to apply that to a more rigid object, a solid object. So go down to the picture below, and instead of imagining a volume of the fluid, now we're going to think about an object that's submersed into the fluid. And the same forces apply. Those forces don't know whether they're acting on a volume of fluid or an actual solid object. So they all apply. There's greater pressure from below supporting this object than there is from above without gravity. Gravity, of course, will balance it out. If the object is less dense than the fluid, it will lift up. So these red vectors I have are gravity. And remember, if the object has less mass, it has less weight, those arrows are going to be smaller, and so the thing is going to accelerate upward. But if this were a heavy object, imagine those red vectors, they would be greater because gravity is greater. They would push down, and there would be a net downward force, and it would accelerate downwards. And this brings us to Archimedes' principle. Archimedes' principle says that the buoyancy force on an object, that's those arrows that are pointing upwards, is equal to the weight of the fluid displaced by the object. And you can see this in its simplest terms in this equation at the bottom of the screen. The buoyancy force equals the weight of the fluid displaced. So F sub B, buoyancy force equals weight. Notice when we're talking about the weight, we have to make this distinction very clear here. We're not talking about the weight of the object. It's the weight of the fluid that's been displaced, meaning the object is there, it has pushed away some amount of fluid. It's the weight of that fluid that is now not present. So again, thinking about this buoyancy force equals weight of the fluid displaced. Let's take our object here, similar to how I showed in the previous video. We have pressure pointing down. We have the pressure plus some additional pressure. That additional pressure is caused by being deeper down in the fluid. We've got the cross-sectional area of my cylinder, we'll call that A, and the height H. And the height is not only the height of the object, but it also refers to the distance between the top and the bottom. The buoyancy force is equal to the difference in the pressures, that delta P times the cross-sectional area. And remember, difference in pressures between two depths is the density of the fluid times G times H, which is the difference in the depths, times that cross-sectional area. We've still got that on the end of the equation. And so the buoyancy force is equal to density of the fluid times G times volume. And again, we have to make this distinction clear. When we're working with these concepts, we have to be clear whether we're talking about the fluid or the object. So here I've got not simply density, not simply the letter rho, but rho sub F, the density of the fluid, not the density of the object. So put those together, we have density of fluid times volume times G, and remember density times volume is mass, and here I've just worked out Archimedes' principle. We started at the top, which is that the buoyancy force is equal to mass of the fluid times G, and that is the weight of the fluid that's been displaced. Let's look at an example in the book, see how we can apply this. Example 15.3 says, you're setting up a raft in a swimming area, and you need to move a 60-kilogram concrete block on the lake bottom. What's the apparent weight of the block as you lift it underwater? The density of concrete is 2,200 kilograms per meter cubed. So you probably know, you probably experienced this if you spent any time maybe in a swimming pool. When you lift something up, maybe you're lifting up a person in the swimming pool, things in a swimming pool feel a lot lighter because there's that buoyancy force. You don't have to exert all the force, all the effort. The water is going to help you out. So here we're going to explore what is the apparent weight of the block as you lift it underwater. It's going to feel lighter because the water is going to be helping you out. Let's first draw a force diagram, just like we learned to do early on in chapter 4, first semester. We have the buoyancy force pulling up. We have the force of the pull, and we have the weight going down. Now, force of the pull, that's how much you need to exert. That's going to be the answer to the question. How heavy does it feel? And going from this diagram to F equals ma, and we're going to replace ma with 0 because we're just assuming not accelerating it, just lifting it without any extra acceleration. So the sum of the forces in the y direction equals 0. Let's take those forces from the diagram and apply them. The force of the pull upward plus the buoyancy force upward minus the weight downward, mg equals 0. We want to solve for force of the pull. So that equals mg minus fb. And now we need to start plugging things in. Well, mg is easy because we're given the mass of the concrete block. Of course, we know g is 9.80 meters per second squared, but we need to figure out what buoyancy force is. So let's apply Archimedes' principle. Buoyancy force is the mass of the water that's been displaced times g. And that is the density of the water times volume. Remember, density is mass over volume, so mass can be replaced by density times volume. And of course, we still have our g right there. Now, we always want to use subscripts to be clear if we have to be clear what the variable is dealing with. So we have force of buoyancy. We have mass of the water, g. We don't have to make any distinctions. It's just g. But notice what I've done here with volume. I haven't specified volume of the water that's been displaced. I've just left it as v. The reason I've done that is I'm about to do a mathematical magic trick here. That volume is, while I use it in this line as being the volume of the water displaced, it is also the volume of the block. If you have a solid block and you submerge it all the way into the water, then the volume of the block is the volume of the water displaced. And so that V, I've left it without a subscript because as I've written to the right in purple, it's both. It's the volume of the water displaced and the volume of the block. So here's the magic trick I'm going to do. I'm going to, in the next line, now think of it as the volume of the block. And so I'm going to replace it. Volume is mass over density, and that comes from the basic equation. If density is mass over volume, you can do the algebra. Volume is mass over density. But notice that it's now, I'm thinking of it in terms of the block. And we need to write those subscripts because notice there's two densities now, and we need to be clear when we're writing which density, which mass we're talking about. So we've still got our density of the water, rho sub W, and now volume of the block becomes mass of the block, m sub b, over density of the block, rho sub b times g. Now we can plug in all the values. The buoyancy force equals, and we've got the density of the water. I'm going to assume that it is fresh water, 1,000 kilograms per meter cubed, over the density of the block, 2,200 kilograms per meter cubed, that's the concrete, times the mass of the block, 60 kilograms, times 9.8 newtons per kilogram, 267.3 newtons. This is the force with which the water is helping us. It's giving a lift. It's that buoyancy force. Now that we found buoyancy force, we'll go back to the blue ink. The force of pull upward is mg minus force of buoyancy. So let's apply those numbers here. 60 kilograms times 9.8 minus the buoyancy force, 267.3 newtons, and we get 320 newtons. And the question is asking, what is the apparent weight? So 320 newtons, but let's compare that with its actual weight. Its actual weight is this 60 times 9.8. And so you can see that a tremendous amount of the weight has been decreased. And as we think back to the original problem asked, it gave us a 60 kilogram concrete block. We can do the math with weight equals mg, and we can see that it is like lifting. The force of the pull is like lifting 33 kilograms in the air. So that's pretty good. A 60 kilogram block only feels like it's 33 kilograms. Now, there's something missing actually in this problem. And I've been comparing it with lifting the block in the air. But you should remember that air is a fluid and air has a buoyancy force. Air has a density of 1.28 kilograms per meter cubed. So really, air gives a little bit of a lift, but it's so negligible that we don't even notice it. So I encourage you to repeat this problem this way. Figure out, never mind the water, just figure out what is the buoyancy force of a concrete block in air and see how much air actually alleviates the weight from us as we're trying to lift something. And you should see, as what your everyday experience is, that the air doesn't really give that much of a lift for such a dense object as concrete. However, it does give a good amount of lift to something that is a density comparable to the density of air, such as a balloon, or even better, a helium-filled balloon. Let's now do example 15.4. This question says the average density of a typical Arctic iceberg is 0.86 that of seawater. What fraction of an iceberg's volume is submerged? Archimedes' principle still holds for a floating object. It doesn't have to be submerged. With a floating object in equilibrium at a liquid surface, the buoyancy force now must balance the object's weight, which will happen if the fluid displaced by the submerged part of the object weighs the same as the object. And this condition determines how high in the water the object will float. So you see this picture that I've drawn at the top. We have some object and it's floating. Now, the buoyancy force isn't going to be as much as it would be if the object were completely submerged, because the only part that counts for the buoyancy force, the only part of the volume, is the volume that's been displaced, this little bit that's under the fluid. And you can see down below an iceberg, and most of the iceberg is, as this problem said, most of it is under the water. So let's see how we can work this out. I've drawn a picture and then a force diagram. We've got our object. Buoyancy force is upward, the weight is downward. Now, if you first drop something into the water, drop maybe an ice cube into the water, it'll go down and then it'll accelerate up and it'll kind of bob up and down for a little bit as it finds equilibrium, but eventually it'll settle, say like in this picture here. So we're looking at where it's settled and it's in equilibrium. We'll draw a force diagram, buoyancy force up, weight down. Here we have F equals ma becomes sum of the forces equals 0. That's the case for equilibrium. And we have the weight of the object is mass of the object times g. These are quantities we're going to be plugging into the F equals ma equation that we'll get back to. So mass of the object, remember, is density of the object times volume of the object times g. And we need to be clear, as I've said before, whether we're talking about the object or the fluid. So density of the object times volume of the object. If you think back to the previous problem with the concrete block, I just wrote V. I didn't write volume of the object or volume of the fluid because they were the same. Here it makes a difference because as you look at the picture, the volume of the object is much bigger than the volume of the fluid displaced. So we have to specify V of the object. Let's think about the buoyancy force. It is the weight of the fluid displaced. So there I have W sub F, which is the mass of the fluid displaced times G, which is equal to, mass is density times volume, so density of the fluid times volume of the fluid displaced times G. Now that we have these quantities worked out, let's apply our Newton's second law, F equals ma, which is now F equals 0. Buoyancy force minus weight of the object equals 0, which means buoyancy force equals weight of the object. And actually, that's just a statement of Archimedes' principle. I'm sorry, not Archimedes' principle, but rather equilibrium, that the two forces are equal and opposite, keeping it in balance. All right, let's make our substitutions. We have, for buoyancy force, we solved up here, it's density of the fluid times volume of the fluid times G equals weight of the object. We solved up here, density of the object times volume of the object times G. It doesn't matter what planet we're on, the G's can divide out. And what we're left with is this very simple ratio. The volume of the fluid displaced, and I'm going to phrase that a different way. It is the volume of the object submerged. So I hope you can see that they are the same. The volume of the object submerged is the volume of the fluid displaced. Over volume of the object equals density of the object divided by density of the fluid. Well, here's why I rephrase the volume. Because we're looking on the left-hand side, that is the fraction or the percentage of the object that is submerged. The problem, in the original question, it says the average density of a typical Arctic, or iceberg is 0.86 that of seawater. What fraction of an iceberg's volume is submerged? So I've solved it in terms of that. The fraction of it that's submerged is equal to the simple ratio of the density of the object divided by the density of the fluid. So in this example of ice in water, V submerged over V object is 0.86 density of the fluid over the density of the fluid. And that becomes 0.86. So pretty neat. Whatever percentage its density is of the fluid, that's going to be the percentage that is submerged. So you look at the picture at the top that I drew. It's not a good representation of an iceberg, but I've drawn it so that about 33% of it is submerged. So what that tells me is if it's in water, particularly fresh water, I know that its specific gravity is 0.33. I know that its density is 33% that of water. Now, let's do another example. Let's take ice. We saw in the previous example in seawater, 86% of it is submerged. Let's put ice in a much denser fluid, such as ice floating in liquid mercury. Now, liquid mercury is very dense. It has a specific gravity of 13.6, meaning it's 13.6 times denser than water. We put ice in it, and um, there's going to be a lot of buoyancy force from just a little bit of displacement. It's going to look something like the picture that you see below, my ice cube in the gray, the silver mercury. Well, let's do the math. The volume submerged over the volume of the object is 860 kilograms per meter cubed. So that is, let's take that as the density of the ice divided by the density of the mercury, 13,600 kilograms per meter cubed. And we get 0.063. So only 6.3% of the ice is going to be submerged. Most of it's going to float on top. And while we generally in life don't deal with ice and liquid mercury, you think about a beach ball that's floating on the water. Most of it is above the water because it has much less density compared to the water. However, some of it necessarily must be below the surface, just as you see in this picture here. There must be some amount below the surface because that amount below the surface is what creates the buoyancy force. However, the denser the fluid, the less of that volume displaced you need. And this brings us to Israel in the Dead Sea. The Dead Sea is very salty. It has a density much greater than that of water. Instead of fresh water is 1,000 kilograms per cubic meter, or let's do it in grams per cubic meter. It's 1 even grams per cubic centimeter. Seawater is a bit more, 1.03. But in the Dead Sea, it is very salty. It has a density of 1.24 grams per cubic centimeter. Now, a neat thing to do if you ever find yourself traveling, visiting the Dead Sea, is floating in the Dead Sea. Now, typically, the human body can float. The average density of the human body, you come to the bottom of my screen, is about 985 grams per cubic centimeter, making it less dense than water, although that depends on body type. Someone with more body fat is going to be able to float better. Somebody who is more lean with muscle and bone and less fat is going to be more dense and might have a lot of trouble staying afloat. It might take more effort and exertion just to tread water and stay afloat. Now, you can see this person here. You can't do this in a swimming pool or any other lake where normally, you can back float. Most people can, but the head has to be down the water. You see this person sitting upright because less of this person's body needs to be displacing the fluid because the fluid is denser. And so floating in the Dead Sea is very easy, and people can float with much of their body above the water. This brings us back to the aircraft carrier that I showed at the beginning of this video. How does such a massive thing, over 100,000 tons of steel with the airplanes and people and everything on board, how does it stay afloat? And the way it does is that much of the aircraft carrier, as you can see of this one that's in dry dock, is under the water, much of the volume. And you can see this red part here. It's a tremendous amount of empty volume of air that you don't see when you're just looking at the ship that's in the water. So it's got enough down here that it's displacing enough water that it's actually enough to hold up the more than 100,000 tons and keep it afloat, despite the fact that the material that the ship is made of is more dense than water. It's got enough buoyancy force. You can do this with an empty soda can. It's made of aluminum. Aluminum is denser than water, specific gravity of about 2.7. But if it's empty and it's got air inside, you can set it in the water, and if you can keep it upright, it will float, just like this ship does. That is the end of section 15.3 on Archimedes' principle and buoyancy. Have a great day.